Okay, so let's move. Mhm. Okay, so let's move to relational data model from conceptual models. Relational is about relations, and relational data model consists of relations. So relation is a relation, that subset of Cartesian product of domains. So let's say address book is a name, then address, and address consists of, let's say, street address and apartment or something. So tuple down there, tuple of Mickey Mouse, Main Street, and a number of apartment. And speaking about domains in relation, we have strings, one string, another string, and third component is integer. So at each record in an address book, each tuple in an address book is a combination of two strings and an integer. And formally, that means that relation is a subset of all the possible combinations of two strings and integer. So instance, in terms of relational tables, instance is a state of the table. So Mickey Mouse, Main Street, and so on, Minnie Mouse and Donald Duck, all the data inside a table, that's an instance or body. Head is a header, so names of columns and their domains, and minimal set of attributes that identify each tuple uniquely. We'll call it a key, and key is a minimal set of attributes. As in most cases, all the attributes, full set of attributes, that's possible to use all the attributes to identify each tuple uniquely. But we want to find minimal one. And one of the keys is a primary. We use it for references from other tables. It's just a matter of decision which key we want to make the primary. In most cases, we want to have small primary key and atomic that consists of single attribute, and preferable of such data type or domain that allows easy to compare values of. So if one key is name and street and something, and another is just telephone number, I prefer to set telephone number as primary key. It's integer, it's simple, it's not complex, and so on. So references would be simpler, not so complex, and easy to search on. Anyway, we'll start before going into relational model details. We start with conversion from interrelationship schemas into tables, into relations. So we have 5 rules, and 2 of them are main rules and other additional. First rule telling us that if we want to convert into relationship schema into relational schema, we need to grasp each entity, student, lecturer, assistant, professor, and look at ellipses, stud ID, name, semester, person number, title, level, and so on, and create just single table for each entity that consists of names from ovals, from ellipses, and mark a key. So student is a table of 3 fields, stud ID, name, and semester. Lecturer consists of lecture number, title, and points, and so on. And key is a key from entity attribute of key attribute. So first rule, how to implement entities in form of tables, is too simple. Next, I think, is how to implement relationships. Relationships are diamonds, may connect multiple entities. Anyway, and some entities may have multiple attributes as in complex keys. Let's say entity 1 has attributes from A11, A12, A13, and so on, and to A1, K1. The whole key for each entity go to table for the relation for relationship. So all the key attributes from E1, all the key attributes from E2, and so on and so on, all the key attributes from En, and all the attributes of relationship itself, but only key attributes from entities and all the attributes from key itself. All other non-key attributes from connected linked entities we don't use here. So let's look at schema. We have requires, attends, tests, gives, and works for. Let's look. Attends, gives, works for, requires, and tests. Attends is about which student attends which lecture. So student ID and lecture number. Gives professor number, person number, and lecture number. Works for assistant person number and professor person number, and so on. The only subtle thing is what attributes, what are the keys. Let's see. Attends has everything marked as a key: stud ID, and number. The same for requires, prerequisite, and follow-up. And other tables are not. So not all the fields, not all the attributes in other tables are subscribed or marked as a key. So let's look what's in common in attends and requires. Both attends and requires are many-to-many relationships. That's why they have all the columns as a key. And all other are multiple, many to one, one to many, one here too. So let's check in relationship of gives, one on the professor side. In works 4, 1 on the professor side. In tests, 1 on the professor side. So let's look here. So many-to-many relationships. All the columns, all the attributes are parts of the key. Every column go to a key. And in one-to-many relationship, one side, person, number, professor, is not part of the key. And many side ID that comes from side of multiple instances is part. So what does it mean? If a professor gives a lecture and the same professor gives another lecture and the same professor gives third lecture, that's completely okay. So professor, the 3 records in a table with the same professor, it's completely okay. So professor should not, we don't constrain professors to give just single lecture. So professor is not in the key, but lecture is. So when lecture, we have a record that lecture number 3 delivered is given by professor number 5, we can't add another record for lecture number 3 and another professor. That's not possible because lectures are unique. So in one-to-many relationships, many side is a part of the key and one side is not. So for each lecture, we may find just single professor, but for each professor there might be multiple lectures. The same thing as for assistants and professor. Each assistant, as it's a key, may present in only single record, and that single record may consist just single professor. So each assistant has only one boss, and professors may the same records with the same professors are allowed. So I have the same professor and the same professor and the same professor and different assistants. Yes, that's good. And the last thing is the tests where grade is added. That's an attribute that's not come from entities. So that's it. So key is a student ID and lecture number that uniquely define professor, person number, and the grade. So that's not possible to have multiple records for the same student and the same lecture for their combination. But with different professors and different grades, that's not allowed. But the same professor may take multiple tests and so on. And the same grade may be assigned to multiple people. So a small question how to call the attributes in relationships. If we have interrelationship with specified roles like prerequisite and follow-up. So let's call it this using this term. So requires, prerequisite, and follow-up. If not, we can use just key attribute names. And in case of ambiguity, we need to add prefixes or something. Like here, both assistants and professors identified by pers and r, person number. So we need to somehow make them different. So we say, let's say we use assistant person number and prof person number for professor. So that's just the rules of attributes calling. So that's it. Third rule. In accordance with first and second rule, we have a database of these records. We have lectures identified by numbers, we have professors identified by person number, and we have a relationship of gifts identified by lecture number, as lecture number should not be, we don't want to have duplicates of lectures, but person number may be duplicated. So looking at this database schema, we see that lecture table and gives table has common keys, the same key, number. And that means that if you want to read everything, all the data about lecture, we need to go to one table of lecture, and search there for lecture by number. And so we'll find title and points. And then we need to go to another table. So that would be a waste of time, of resources. Why don't we merge them and have just single table, lecture, number is a key, the same, the common key, title, CP, and personer here. As each lecture is given by just, we know that each lecture is given by single person. That's simpler, and probably that's better in case of one-to-many relationship. So we may, for each lecture, we have just single professor. Let's take professor ID and add to lecture table. And we don't need to store this extra table with pairs. So that's more compact. Our queries will run faster, queries to lecture, and so on. But we can't merge relations professor and gives. They have different keys. So that's not possible. We may merge relations only with the same key if we prefer. Why we may don't want to merge? That's possible too. In cases when we have different tables, different relations with the same key, but we understand that workload or patterns of queries are different. In some queries, we read lectures, we search for data from lecture table, and completely different queries, we'll search for professors who give lectures, and no queries address both tables at the same time. So we have no queries that need to go here and there. Probably that would be better to store both tables accessed differently in different situations by different queries separately. So when we read a table of lecture, we get from hard disk or from other storage just this volume of data, just title and CP, and that's everything we want. But as in this case, all the data will consume space in the same record probably, and it will, and database management system will read the whole record with all the fields, and we don't need it. We need just few fields, few attributes, and we don't need that personer. And if we can predict such a pattern of use of our system, lectures will be searched differently by different queries, and gives will be searched by another queries. Then it may be beneficial to store them in distinct tables. But in the common case, that's better to merge them. So instance of professor and lecture, we have a table of professors, and we have table of lectures together with added to table of lecture has its own native number, title, and points. And we add just single column of person number that links, then semantically links. That's not technical. That's not technical reference. It's just a number, and if we want to understand who deliver a lecture on ethics, we need to get this number and search for it in another table. So we can't go directly to a record. That's not a reference. It's just a value, and we need to compare all the values and find what we search for. So that's Socrates. Okay. And in the reverse direction, that will not work. We can't embed lecture lists or collections in professors. We may finish this table like this. So Socrates, who gives this lecture and that lecture and that lecture and that lecture, multiple records or something else. So that's not a relational way to do. And each professor has multiple lectures to deal with essentially unlimited set of even identifiers. It's much more harder than embedding professor ID, just one value, atomic value, into new column in a lecture table. So yes, if we'll try to do so, to do this, then we'll run into anomalies. We'll break the key. So person number is no longer a key, duplicated. And so we revisit the situation when we'll be speaking about normal forms. So add two more rules for special situations. Is a employee, professor is an employee, assistant is an employee. So how to implement it? First way is to coming from top to down of this tree. We just create tables. Employee of person number and name, here it is, and then professor. The professor has room and level, but have no identifier. Let's borrow it from employee. So professor is an employee, so it has person number 2. And assistant, this is the same thing. That's one way. But this schema is not too good from the performance point of view. If I need to collect all the data of professor, I need to search in 2 tables. I need to go to professor table, search by person number, and I'll have level and room. And then I need to go to employee table and search for name. The same thing. Maybe it's better to merge them, but we can't merge them finally, as our system may keep data on another employees who are not professors and not assistants. So employee table remains, but we merge a name field into professor. So queries become more performant to search for professors or data, but we run into a risk or possibility of collision, or as this data structure allows for putting different values in records with the same key. So if employee with person number 1 to 3 is a Socrates, and professor with person number 1 to 3 is an Archimedes. So that's possible to put different values here and there in records with the same key. And there is no restrictions or other limitations how to check it, how to enforce it. So names should be the same. One may say, oh, that's my program. Who enforce it? So I have a screen or a dialogue in my program or something where professor data should be entered. And at the moment my program received a new professor data, it go to both tables and change them synchronously with the same data. So put same data to both tables. But what if another team or another programmers or something will create another program for the same database, and without having in mind this restriction? And then they may occasionally allowed to occasionally spoil the data. So putting different names in different places. So this database schema is much more safe. No program and even no database administrator may create a duplicate or may create different names for the same person. If person number 123 is Socrates, then the data is kept only in employee table and nowhere else. So it's much more safe than this situation. But performance, query performance better here. So we need to choose, and relational model prefer this way to work and deal with performance problems differently using other methods, using, let's say, views or materialized views, essentially caching and so on. But structural safety is preferable in most situations by relational model. So we want to have our database structured that way. So there is no possibility to put incorrect data or put contradictory data. So, and this feature or this property is much more wanted than just being fast. We can run fast, make something run faster, but we can't make something safer starting from this situation. And the last thing is last rule is a weak entities, how to implement it this way. So having a weak entity and identifying relationship, we merge them. So exam is identified by student ID and a part number. So that's a key. And exam together, this takes relationship is merged in single table. And then covers lectures covered by exam. Multiple lectures may be covered by different exam instances by different students, and the same exam is for, and some exams are for different lectures. So covers relationship is linked to entity of lecture with number, and number is here, and to exam. And to identify exam, we need stud ID and part. That's why our table of covers for covers relationship consists of stud ID, part, and number, and lecture number, and everything as covers is many to many, and all the fields, all the attributes are parts of the key. The same for gives relationship. Just few. Let's skip this. Let's speak about this on our seminars, but you may look and is it possible on questions? Is it possible to implement entity relationship not in relational model, not in tables, but in just objects? Yes, that's possible. So conceptual model is quite high, lays on quite high abstract layer or level. So we can implement it in just objects. And how to implement generalization is A. And yes, that's possible to do it differently. We can use native inheritance of Java, or we may implement it using delegation. So that's it. So let's stop with this and look at final relational model. So we have professors, we have students, and lecturers together with professors who give it, and assistants together with bosses. So two relationships are merged into relationships of one to many are merged to many side to entities on the many side, and many to many relationships can't be merged, so requires and attends here, and tests too. That's structural issues, or how to create a relational database schema, starting, let's say, with conceptual model of entity relationship. But what to do with it? Yes, we define tables, we fill it with data, but what next? How to answer queries, and what queries are possible? One answer is relational algebra, and relational algebra is a set of operations that allows to build new tables out of base tables. So we have base tables, and then applying operations to result of previous operations, and so on and so on. We may build some tables, trying to build an answer to our query. So query may be expressed as relational algebra expression, and that's operations. So each operation has arguments. Let's say selection may be applied to a table, and selection has a condition. So result of selection applied to a table is just another table where all the records, where all the tuples follows that condition, adhere to that condition. The same with projection and Cartesian product and everything. So it's joins of different kinds, unions, intersections. So let's look. What's a relational algebra? Relational algebra is an algebra, and algebra is operation is a set of operations over some objects and we have basic operations called atoms, and most basic expressions called atoms, and most basic expression is just a name of table relation. I have a table of student, so that's expression. If I run this query that consists of just an atom of student, answer is just contents of student table. So essentially that's a query of please show me all the students. So name of relation is an atom. Some relations we may have constant relations, and relations relation of student is not constant, that's dynamic. We may add new students, delete some previous records, change them, and so on. But we may have some relations that's constant and consists of, let's say, just one record of this value, and that's possible to use too. But in most cases, we have atoms, just relation names, and operators that build composite expressions, selections. Most names of operators come from Greek alphabet. So selection is for Greek letter sigma, small letter sigma, for S. So selection and sigma. And expression, we may apply selection not just to a relation, but to another composite expression. So that's why E1 here. And in simplest case, that's just an atom. And P in index is a condition. We need to check. Projection for P, for Greek letter P, for projection, big letter, and list of column names or list of attributes in index. And projection create a more narrow table. A selection create more short table in terms of number of records. Projection creates more narrow table in removing some columns, removing some attributes. Cartesian product is a Cartesian product, all the combinations of attributes from both tables, and each and every expression results in a table. So we may think about E1 as a table, be it an atomic relation or a composite relation or result of composite expression. The same thing here. Another function is rename. We may assign new names to attributes, or the complete list of attributes, or just rename few of them. We want to rename B into A, let's say, column B into A. Union is a collection of all the records from first table and add records from another table. So we just combine records from different tables. And minus is, we want to find only records from E1 that not present in E2. That's minus or subtract operation. So let's look at selection, projection, and other operations. Selection from table of student using condition of semester is greater than 10. So let's say something like this. So Xena creates from semester of this, Jonas from that, and that's it. And all other students, we have no students here with semester greater or equal of 10. Result is correct, probably. We use projection to restrict table to just few columns. If you want to find only levels of professors, you may say project table of professors using level column. Let's look at professor table. Professor table has multiple columns, and level consists of FP, full professor, associate, full. So values in a level column are not unique. We have multiple full professors and multiple associate professors. After projection, all duplicates are removed. So projection not only cut a column, but it also removes all the duplicates in results. So that's it. Speaking about Cartesian product, if we have two tables of, let's say, 3 columns and 2 columns, result is 3 columns from first table, 2 columns from next table, from second table, and all the possible combinations. First record from here with first record from there. First record from here and second record from there. Here it is. And vice versa, and so on. Second record from L table with tuple, first tuple of R table, and second tuple of L table with last tuple of R table. 2 multiply 2 results in 4 different tuples. That's Cartesian product. Let's build a Cartesian product for professor and attendance. We have professor, attendance, and as professor and attendance, they're completely different things. So attendance is about lecture attendance, and professor are about professors. All the combinations of every attend record and professor. So Socrates with some attendance record. Socrates with another attendance record. Kant with another, and so on. So that's a quite huge result set. Let's look at how much. 3. We have 6. Oh no, 7. We have 7 professors and a table of attendance of 3, 6, 8, 10, and 12. And 12 attendance records. So size of professor Cartesian product to attendance is 84. 7 multiply 12. So 84 records. in result of this Cartesian product. Not too much sense to generate such a result. Why do we want to have such a table? What for? Professors and lecture attendants. In most cases, we use Cartesian products not to just to generate all the possible combinations, but to filter on next step. If professor, let's say, gives have something in common, then we may compare some fields of Cartesian product and select using this condition. And the result of and such an operation is called join. Joining of a table is logically equivalent to creating Cartesian product of both tables and then applying some conditions to fields to attributes from first table and second table. Somehow compare it not only on equality but on different conditions. So let's say we have two relations. First relation R with some fields, and second relation S, and some fields are the same. So A1 and AM are on individual attributes for table R. C1, C2, and so on are special for table C, and B1, B2, B3, BK are common for two relations. It's just name of fields. And join operation is essentially, it may be expressed in terms of other operations. So we may build a Cartesian product and then apply selection using a set of conditions. B1, column B1 from R should be equal to column B1 of S. B2 should be equal to B2. B3 should be equal to B3. BK from here should be equal to BK from there. So in every combined record from two tables, we check B1 from here, B1 from there. Other is the same. Oh no, so that's not, we don't want this record. We search only for equivalent values in appropriate columns. And then we don't want to have in this result of this expression is all the columns from R plus all the columns from S. So we have duplicates of columns, B1 from here and B1 from there. And then projection leaves only one instance for each B1, B2, and BK. So that's a join. And the join called natural join. And Mark is look at this Mark we don't, for natural join, we don't supply, we don't set no conditions. It performs automatically. It searches for columns with the same names and use them in a condition. So if two relations under natural join has no common fields, so result is just Cartesian product, and that's all. If they have all the columns being the same with the same names, so all the columns with the same names will be used here. So we have no in selection. We have in subscript index. We have condition. In natural join, we have no conditions, just operation, and that's it. So yes. So yes. Some fields in the result come from R, that's A fields. Some fields come from S, that's C fields, C1 and so on. And some fields are coming from intersections that are common to R and S. Natural join may be performed in multiple ways. So student and attends, and then join with a lecture. And result is all the data from students, student ID, name, semester, then number of lectures that come from attendance, the attendance record, and then join lecture. But if we stop here, join attendance, then we'll have just this 4 columns. And then if we join lecture, and to join lecture, number of lecture will be used. So student and attends has a student ID in common. Attends and lecture has number in common. So natural join will use number to essentially look up a lecture that describes this attendance record, and add title and so on and so on. So natural join may be performed in multiple steps. But in the common case of join is called theta join, and theta join is a join over condition. So we say R join and condition. And condition, and essentially result of this join is Cartesian product and selection over this condition. So we need to provide conditions, what to compare and how to compare. A natural join, we don't provide anything. So that's theta join, where we manually set some condition. Let's say A1 is greater than B2, or A2 is equal to B5 plus B7. So any condition may go. So natural join for tables ABC and CDE of this data. Let's check which columns are the common. Only C. A, B here, D is there, and column C is shared. So let's compare C1 here, C1 here. So result consists of A1, B1, C1, B1, E1. So here it is. C2, we don't have C2 here. So nothing no record to the right to merge or to glue to this part. C3 here, nothing to the left. So the only answer in the record is this. And all other values has no equivalent value to the right. And some kinds of joins called outer joins are proposed and used to be sure that every record, let's say from left side, from left table or right table, that every record in case of left outer join, all the records from left side will be represented in the result. In some cases, we'll find a corresponding record, like here. And in some cases, for C2, for the second record, we can't find the corresponding record from the right side. Let it be. So we'll just put nulls or empty values, somehow mark values, but result will contain a record with values from the second record. Let's say I have people who perform some tasks, and some people do something, and they have tasks performed in second table, and some people don't perform any task. So I have a person in left table, and I want to find those persons who didn't do anything, who didn't perform a task. And exactly this, I perform left outer join, and I have records for people who do something with task descriptions, and people who has no task descriptions. And these are exactly that people I want to find, and then come and speak with them. Right outer join, the same thing. Result contains every record from the right table, and in some cases it has corresponding record to the left, and in some cases it have no corresponding records to the left. That's right outer join. And full outer join, that's union of left and right outer joins. So every record from the left table represented in the result, A2, B2 with empty fields, and every record from right table is represented in final result. Here it is. That's called full outer join. And probably the last, not the last. Yes, that's a special operation called semi-join. And semi-join is an operation that just search for corresponding record, but don't include data from corresponding record in the result. So if I perform left semi-join for these tables, result is A1, B1, and C1. As for record of A1, B1, and C1, there is a corresponding record, the first record from R. But I don't need, I want just to be sure that something correspondent is here. And I don't need values from there. I don't need data from there. I need to find only records that has something that has something correspondent in the right table. The same with right semi-join. Everything from the right table that has corresponding record to the left. So result is here, and only columns from the right table. So that's our join variants, and join generate tables bigger than source tables. In some cases, just so all the columns from left table, all the columns from right, minus duplicates. So C is only present once. So that's joins, and rename. Okay, so rename operator. It's rename fields. It may rename the whole relations. It may assign new relations, new names to relations. Let's say I have table of requires and I need to use it twice. So if I can't refer to it, if I try to refer to table of requires, so how can I build a condition? Requires dot field equal to requires dot field. How to differentiate them? So rename allows to rename first instance of requires into, let's say, L1, and second instance of requires into L2, and then use essentially LSs for this instances and say I need to check that L2 follow up is equal to this and L1 follow up equal to L2 prerequisite. So that's simple to express anything. If I rename the same instances, and in some cases I may rename just attribute names. Let's rename prerequisite name of column into or attribute into required. That's another thing. Intersection of two tables. Oh, that's intersection. That's finding common records in both tables. Result is the common record in both tables. It may be empty if no common records, and it may only work if both relations with the same schema. So let's say I want to find data, a list of professors from lectures, this part, and go to table of professors, extract only full professors, select only full professors, and have just a column of professor number. And let's find intersection. So essentially, this result is a list of professors identifiers who give at least single lecture and are full professors. So assistant professors not present here, and professors, even full professors who don't deliver lectures at this moment, are not in the list. Intersection may be simulated like this: R minus S and R minus this result, like in set theoretic operation. Quite complex operation called relational division, and you may try to, so that's reverse operation for join. If join is something like multiplication, we build we multiply essentially two tables and then extract something. Division is reverse operation. We want to find a table. Result of relational division is a table. If we join it with divisor, then we'll find a table we divide. So a tens divided by something is such a table that being joined with right part of this expression, the result of that join or not join, Cartesian product, just multiply it to this, results in a tens table. So not all the tables may be divided. So let's look here. I'm trying to divide this column or this table on this value. Only value M1 that has record of M1 with V1 and M1 with V2 go to result. And let's say and V3 is not, we don't consider it, and M2 don't go to result as it has V2 but don't have V1. So division can be simulated with other operators, and it's quite not frequently used as an operation, as an operator for division. So let's skip it. You may look at these operations. An other way to express essentially the same thing, a relational algebra is algebraic, is expressions built of operations that's constructed. We tell the system what to do. You need to select, then you need to join, then you need to do something, then you need to do something. And calculus is about setting predicates. I want to search anything where predicate is true. So I want to search all the objects of P such that P is a record from professor as a tuple from professor table, and P dot level is equal to this. So, or I want to find students who attend at least one lecture of given person of Curie. So I want to find such objects. Each object is a student tuple, and there exists another object from table attends with such condition and such a lecture, and exists an object from lecture table. Exists a professor such that professor's number is the same as lecture professor, and professor name is a Curie, and lecture number is the same in attendance record, and student who attended that lecture is the same as this student. So if all the conditions are met, then student is part of result. If not, then not. So essentially, relational calculus is a declarative expression or logical expression of what should be found. We don't tell what to do. In relational algebra, we tell what to do. Select, join, project. Here, just conditions and some existence conditions. There are two variants of relational calculus, tuple variables and domain relational calculus. We'll return to notions of relational calculus on, oh no, let's not return. So tuple version of relational calculus consists of atoms and formulas. So tuple variable is a variable that may have a value of a tuple from some table. So we say S is a tuple from table R. And another atom is saying that I have a tuple variable, a field, an attribute name, and some operations of some comparison. SA is greater than TB, or SA is equal to some constant, or greater than constant. Everything are atoms, just tuples, and tuples are restricted by some conditions. And then all atoms are formulas, and we may add negation in front of formula, and we may put legal formulas in round brackets, and we may build a complex formula using so and or imply and use for every variable and exists. So that's for tuple. And domain relational calculus different, a little bit different. We need to domain relational calculuses. Let's leave it to our seminar. And the last thing is a Code theorem. And Code proved that all the three languages, relational algebra, safe expressions from tuple relational calculus, and safe expressions from domain relational calculus, all are equivalent. So if we have, what does it mean? As SQL is based on relational calculus, SQL is a language. What we write in SQL expressions that's essentially relational calculus. But implementation of SQL is based on relational algebra. And their equivalence means that everything we write as terms, execution plan, implementation of this SQL command, SQL expression based on relational algebra, we may find equivalent relational algebra operator expression that run system to a result. So system can't run declarative, something declarative. Our systems are constructional. We need to run operations by operations. But query is declarative. So declarative query in relational calculus converted to a sequence of operations in relational algebra, and that's proved that they may be equivalent. That's possible to translate there and back again. So that's main one of impact theorem. Relational algebra and relational calculus have the same expressive power. And so everything that's expressed in one of the languages may be expressed in another. So I think we'll stop here for today, and the task on practice is to use our rules to convert ER models into tables. So let's stop for today and meet you next time. Thank you.
Thank you. See you.
Bye.
Thank you. Bye.
Bye.